Hello, Matthews Gatos here. In this lesson, we're going to look at part 1 of 5.5 graphing functions. So this is where everything we've been working on this chapter comes together in one beautiful lesson. So before we get too far into figuring things out ourselves, I wanted to give you an example of what a graph might look like if you were given some information and that hard, heavy lifting work was done for you. So for example, if we have a function that is continuous, and that just tells me there's no vertical asymptote, and differentiable, which tells me there's no kinks, corners, or cusps for all real numbers. Now, it's giving us information on the first and the second derivative, and that will be enough for us to graph everything. So the first derivative is 0 at -3, 1, and 4. So that means that I'm going to expect to see a max or a min at any of those points. To know whether there's a max or a min, I need to go to intervals of increase and decrease. So here it says that the first derivative is positive, meaning increasing from -infinity to -3 and between 1 and 4. It is decreasing because it's less than 0 in between -3 and 1 and 4 to positive infinity. So that tells me that at -3, if I'm increasing to the left, decreasing to the right, I have a max at -3. I'm decreasing to the left, increasing to the right, which means that this is a min. And increasing to the left, decreasing to the right, this tells me this is a max. Okay, let's look at the second derivative now. The second derivative is 0 at -1, 3 and 2, 4. So those are my points of inflection. And I can just note those on my graph. So -1 and 3, that is an inflection point. And 2 and 4, that is also an inflection point. Okay, so that means that it is a concavity change. So to figure out what the change is, let's look here. It is greater than 0, which means concave up between -1 and 2. And it is negative or concave down between -infinity, -1, and 2 and positive infinity. Okay, so let's put those together on the graph. So now that I have the inflection points, let's go back to the maxes and mins. I am not given a y value, so I don't know exactly how high or how low the max and min reach. So I'm just going to draw it based on an estimate. So at -3, I have a max. So -3, I have a max. So I'm just going to draw it to be above this inflection point. So let's say there, and that would be a max. And then at +1, I have a min. So right here, I'm going to have a minimum. So I'm just going to make it in between my inflection points. Let's say right there, and that would be a min. And then I have another max at 4. So I'll just make it past that inflection point. Let's say there. Okay, so now piecing those together, let's go to the concavity to do that. So it's concave down, -1 and beyond. And there's an inflection point right there at -1. So I know that everything past or to the left of -1 will be concave down. So it's going to look kind of like that. It's also concave down to the right of 2. So that's why there's an inflection point here. So it's concave down. So I'm going to kind of come up and go around. So it's part of the frown. And it's concave up in between that. So I'm going to connect these two inflection points going through the minimum like that. That would be concave up. So that is one example of what the graph may look like. Again, the answers may vary depending on how low or how high you put your graph to be. So let's look at how we graph a function given its equation. So we're going to be determining things from the original function, from the first and the second derivative. So in the original function, we're going to be able to determine the domain, the x-intercepts, the y-intercepts, and asymptotes. Those would be vertical asymptotes, horizontal asymptotes, and slant asymptotes. And also from the original function, I can test whether functions are even or odd. If they are even, they are symmetrical about the y-axis. So in other words, there's been a reflection in the y-axis. If they are odd, they are symmetrical about both. So there's a reflection in the x and the y-axis. From the first derivative, From the first derivative, we can find our critical values by setting our first derivative equal to 0, or when our first derivative is undefined, and then look for intervals of increase and decrease, which will of course tell us our max and mins. In the second derivative, setting the second derivative equal to 0, we will get key points. And based on those key points, we can look at intervals of concave up or concave down. Of course, in between concave up and concave down would be a point of inflection. Now remember that this point must be defined in the original domain. So for each of these questions, I'm going to use this table to kind of help me organize my results. And I'll go through doing function first, first derivative, and then second derivative, putting it all together on a graph. So we're going to do 3 examples in part 1. So let's look at our first example. I have x squared over 1 minus x squared. The very first thing I notice is that I have a domain restriction that x cannot be positive and negative 1, which tells me I'm going to have a vertical asymptote at 1 and at negative 1. So I can kind of just jot those in. So I've got a vertical asymptote at 1 and a vertical asymptote at negative 1. So I want to look at, well, we're talking about vertical asymptotes. Let's look at the behavior about the vertical asymptote. So I'm going to take my function and I'm going to write it in factored form. So I have x squared over, factoring out the negative 1, I have a difference of squares, because then that would be x squared minus 1. Okay, so you have your critical values at 0. That would be your x and y intercept in the numerator. We can denote that up here. And of course the restrictions of the denominator, 1 and negative 1. So looking at this function, I see that this is a negative 1, so it will be negative in each of the intervals. And x squared will always be positive in each of the intervals because squaring a number makes it positive. So I really only have to focus on these factors. X minus 1 is 0 here, so to the left it's negative and to the right it's positive. And then x plus 1 is 0 there, so to the left it's negative and to the right it is positive. So putting these all together, here I have 3 negatives, which means that I am negative, which means to the left of negative 1, I am going towards negative infinity. Here I have 2 negatives, so it's a positive. So to the right of negative 1, my end behavior is towards positive infinity. In between 0 and 1, I have 2 negatives, which is positive. So that means to the left of 1, I am going towards positive infinity. And here I have 1 negative, so to the right of 1, I am going towards negative infinity. So that's my end behavior for my vertical asymptotes. Let's see if we have a horizontal asymptote. So to figure out a horizontal asymptote, I want to use long division on my function. So I'm going to do negative x squared plus 1 divided into x squared. So looking at that, I have x divided by x squared is negative 1, multiplying it through x squared minus 1, subtracting, and I have a remainder of positive 1 because 0 take away negative 1 is 1. So that means my function x squared over 1 minus x squared is the same as negative 1 plus 1 over 1 minus x squared. So this is my horizontal asymptote. So I have a horizontal asymptote at negative 1. So I'll just mark that on my graph like that, and I'll note it up in my table. Now, if I have a horizontal asymptote, that means I do not have a slant asymptote. I can't have both. Let's look at my end behavior. That's what this is telling me. The remainder is my end behavior. So I'm going to look at the limit as x approaches positive infinity of 1 over 1 minus x squared, and the limit as x approaches negative infinity of 1 over 1 minus x squared. So in this first example, if I were to put in a positive number, I would have 1 over 1 minus a really big positive number. So that is going to be negative, which means my right end is going to be below The curve will be below the horizontal asymptote. If I put in a negative number, I'm going to have 1 over 1 minus a negative number squared is still positive. So if I have 1 minus a really big number, it's still going to be negative. So that means my left end is also below. So I have the behavior around my horizontal asymptotes and my vertical asymptotes. The last thing I need to do is figure out if I have an even or an odd function. And I'm going to do that by looking at f of negative x. So if I have f of negative x, I have negative x squared over 1 minus negative x all squared. So f of negative x is equal to x squared over 1 minus x squared. Well, that's just f of x. So since f of negative x equals f of x, my function is an even function, which tells me it's symmetrical about the y-axis. So look at all of that work, and I'm only in the original function. Now I'm going to look at my first derivative. So here's all the information that I just found out. Now I'm going to look at my first derivative, and that's going to tell me intervals of increase and decrease, and then maxes or mins. So my first derivative is 2x over, now let's factor this so I can take out a negative 1, because then it will be x squared minus 1 all squared. So this will be 2x over, negative 1 squared is just 1, and x squared minus 1 is a difference of squares, x minus 1, x plus 1, and each of those will be squared. Okay, so that is my first derivative in factored form. So let's look at the critical values. In the numerator, I have a critical value of 0, and in the denominator, I have restrictions of positive and negative 1. So setting up my number line, remember that negative 1 and positive 1 are not defined in the original function because they are vertical asymptotes. Let's look at the intervals of increase and decrease for this. Okay, so for 2x is 0 at 0. So to the left it's negative and to the right it is positive. Now each of these here, when they're squared, when I have any kind of a number squared, it is always going to be positive. So it might be negative on the inside, but once I square it, it's positive. Same thing here, also positive. Okay, so in my first interval, I have 1 negative, which means I'm decreasing. In my next one, I have 1 negative, so I'm also decreasing. I have all positives here, so I'm increasing, and all positives here, so I'm also increasing. So looking at my intervals of increase and decrease, my intervals of decrease are from negative infinity to negative 1, or from negative 1 to 0. My intervals of increase are going to be between 0 and 1, or 1 and positive infinity. Okay, so let's look at to see if we have a max or a min anywhere. So here vertical asymptote, so nothing there. Here vertical asymptote, nothing there. At 0, see how I'm decreasing to the left, increasing to the right? That tells me I have a minimum at x equal to 0. So when I have a minimum at x equal to 0, let's figure out what the y value is, back to my original equation, and plug in 0. And that's just 0. So that means at 0, 0, not only is it an x and y intercept, it is also a minimum value. So I have a minimum at 0, 0. So let's go on to my second derivative to look at intervals of concavity, and then we can put that all together. Okay, second derivative right there, let's put it into factored form. So second derivative, I'll factor out a GCF of 2. And then I'm left with 3x squared plus 1 all over 1 minus x squared, which is really a difference of squares. So maybe I'll write that as a difference of squares. 1 minus x, 1 plus x, and each of them will be cubed. So cubed and cubed. So for my second derivative, looking at this, actually I'm going to do this so that I have a negative leading coefficient taken out. let's try this again, a little bit better way here. So I'm going to factor out a negative 1, x squared minus 1. For my intervals, I want my leading coefficient to be positive. So let's try that again, similar to what we did on the last one. So the second derivative is 2, 3x squared plus 1 all over. Negative 1 cubed is negative 1. And then I'll have x minus 1 cubed and x plus 1 cubed. And I'll put that all together. Okay, so in my intervals, I have on the top, no x-intercept. In the bottom, restrictions of negative 1 and positive 1. And again, remember those are vertical asymptotes. So I just want to remind myself of that. Okay, so in the top, 2 times 3x squared plus 1. This is always going to be positive because when I square a number, it's positive. Times by 3, still positive. Add 1, positive. Times by 2, still positive for all of the intervals. Okay, in the denominator, I have a negative 1, so that will be, because it's a constant, negative in each of the intervals. X minus 1 cubed, that is 0 at positive 1. So to the left, it's negative, and to the right, it is positive. And my last factor of x plus 3, that's 0 at negative 1. So to the left, negative, to the right, positive. So here I have 3 negatives, which makes it concave down. Here I have 2 negatives, which is positive, concave up. And here 1 negative, so it is concave down. So my intervals of concavity, I am concave down from negative infinity to negative 1, or from 1 to positive infinity. I am concave up between negative 1 and 1. So because I have a concavity change from down to up or up to down, you would expect to see an interval, or sorry, a point of inflection. But there is no point of inflection because negative 1 and positive 1 are vertical asymptotes. So this has no point of inflection. But now, based on my intervals of concavity, I can do my graph. So let's look at the ends of the graph. So between negative infinity and negative 1, it is concave down. So if I look here, I'm going to connect my arrows for my end behavior, but I'm going to be concave down. So that's the first part in here. Then beyond 1, I'm also concave down, and I connect my end behavior, but I'm still concave down. So something like that. In the middle section, I'm concave up between negative 1 and 1, connecting the end behavior, going through my minimum point and up like that. So I should expect my graph to look like that. So a lot of work for just one graph, but we did it all without using the graphing calculator. Let's check on the graphing calculator to see if that is in fact right. So looking at the graphing calculator, you can see that my graph looks pretty reasonable compared to what I did. Okay, let's look at a second example here. So again, we're going to follow all of those steps again. So starting with my base function, we're going to find the intercepts, the asymptotes, and is it even or odd. So looking at this, I have x squared plus 1 in the denominator, which means x is an element of the reals, meaning there is no restrictions, so there are no vertical asymptotes. To figure out the intercepts, let's let x be 0, then I'll have 0 over 0 plus 1, which is just 0. So I have an intercept at 0, 0, an x and a y intercept. Okay, for horizontal asymptote, let's use long division, x squared plus 1 into x. So x divided by x squared, that's 0. 0 times all of that is 0, subtract is x. So what that means is x over x squared plus 1 is 0 plus x over x squared plus 1. So in this case here, the 0 will be my horizontal asymptote. So I'll note that here, horizontal asymptote at y equal to 0. And then I can look at the end behavior here to figure out what's going on. So the limit as x approaches positive infinity of x over x squared plus 1. So if I put in a positive number, I'm going to have a positive over a positive number squared, plus 1 is still a positive. So altogether, that is positive. So at the right end of my graph, I am going to be above. Okay, then I'll look at the limit as x approaches negative infinity, and that will be of x over x squared plus 1. So if I put in a big negative number, my numerator will be negative. A negative squared is a positive, plus 1 is still a positive. So altogether, that will be a negative. So the left end will be below. My curve will be below the horizontal asymptote. So up here, I have a horizontal asymptote at 0. If I have a horizontal asymptote, I do not have a slant asymptote. I can't have both. So the other thing I need to figure out is even or odd. So looking at this, I'm going to look at f of x, or f of negative x, which is equal to negative x over negative x squared plus 1. So f of negative x is negative x over x squared plus 1. Now that is not f of x that I started with, so I'm going to try and factor out a negative 1. And then I get x over x squared plus 1. Now that is f of x. So what that says is f of negative x equals negative f of x. So since that is true, I know that f of x is odd, which means it's symmetrical about the x and the y axis. Okay, now let's look at the first derivative. So here I have all the information I've had before, and I'm going to look at the first derivative, which is intervals of increase and decrease. So looking at my first derivative, let's factor that. So take out a negative leading coefficient, and then I have a difference of squares all over my denominator, which can't be factored. Okay, so I have a critical value in the numerator, an x-intercept in the numerator, which is the critical value, of 1 and negative 1. No restrictions in the denominator, so my critical values are just negative 1 and positive 1. So looking at my first derivative, this is always negative because it's a constant. My denominator is always positive because it's squared. In the numerator, I have an x minus 1, which is 1. So to the left, it's negative. To the right, it's positive. And then x plus 1 is 0 there. To the left, it's negative. To the right, it is positive. So looking at my intervals of increase and decrease, I have 3 negatives, which means this is decreasing. 2 negatives makes a positive, so that's increasing. 1 negative means that is decreasing. So my intervals of increase are from negative 1 to 1. My intervals of decrease are from negative infinity to negative 1, or from 1 to positive infinity. Okay, so if I decrease to the left, increase to the right, that means that I have a minimum at negative 1. So in my original equation, negative 1 over negative 1 squared plus 1, that all ends up being negative 1 over 2. So that means that I have a minimum at negative 1 and negative a half. So I can put that one on the graph. So at negative 1 and negative a half, right about there, I have a min. And then if I increase to the left, decrease to the right, I have a maximum. And that maximum value occurs at 1. So 1 over 1 squared plus 1, and that equals 2 a half. So I have a maximum at 1 and a half. So putting that into my graph, 1 and a half right there, I have a maximum. Okay, so we're going to add to this graph a little bit more by looking at the second derivative and intervals of concavity. So for the second derivative, it's listed over there, and all I have to do is factor it and then look at my key values. Okay, so in factoring this, I'll take out a greatest common factor of 2x, and then I'm left with x squared minus 3. So when I have x squared minus 3, that's just a difference of squares, which is x minus root 3 times x plus root 3. All over, in the denominator, I just have x squared plus 1 all cubed. Okay, So I have critical values, or sorry, key points at 0 and positive and negative root 3. So 2x is 0 right here, and to the left it will be negative, and to the right it will be positive. X minus root 3 is 0 right there, so to the left it's negative, and to the right it's positive. X plus root 3 is 0 there, to the left it's negative, and to the right it is positive. And my denominator here is always going to be positive, since I have any number squared, which is positive, plus 1 is still positive, and cubed is also still positive. Okay, so in my first interval I have 3 negatives, which makes this concave down. Then I have 2 negatives, which is making that concave up. Then I have 1 negative, so that's concave down, and all positives, which is concave up. So intervals of concavity, so it is concave up between negative root 3 and 0, or root 3 and positive infinity. And it is concave down from negative infinity to negative root 3, or 0 to root 3. Okay, so looking at this, I don't have any restrictions in my original domain, so it looks like I have an interval point here, here, and here. So 3 different inflection points. So if we look at this, I have an inflection point at negative root 3. So putting that into my original equation, I would have negative root 3 all over negative root 3 squared plus 1. So that works out to be an inflection point at negative root 3 and negative root 3 over 4. Then I'll put in my other point, 0. So I'll have 0 over 0 squared plus 1. So an inflection point at 0, 0. And then putting in positive root 3. I end up having an inflection point at root 3 and root 3 over 4. So to help me out, I just kind of want to know what the number value of those are. So negative root 3 and negative root 3 over 4. I'm going to plot where that is. That's about at negative 1.7 and negative 0.4. So an inflection point right about there. And then an inflection point at 0, 0. And an inflection point at about 1.7 and 0.4. So that's going to be just below my maximum value. We'll say right about there, inflection point. Okay, so putting this all together, let's look at our intervals of concavity. So to the left of negative root 3, it is going to be concave down. So looking at this is going to be concave down and kind of going out to my end point. It's also going to be concave down between 0 and root 3. So going from 0 up to my maximum and through that inflection point. And then we'll do our concave up. So our concave up between this inflection point and the next inflection point going through the minimum, so like that. And then from the inflection point towards my end behavior, also concave up. So something kind of like that. So a bit of a wonky sketch, but all the key parts are labeled in there. So again, I always like to check that on the graphing calculator just to make sure that I'm doing that okay. So going here to the graphing calculator, I can see that works out really nicely. Okay, in my last example here, we're going to follow that whole process again. So let's start with our function, x squared minus 1 all over x cubed. So again, notice I have a restriction that x cannot equal to 0. So I know I'm going to have a vertical asymptote at x equal to 0. So I'll just label that on my graph right away at x equal to 0. Okay, so I want to take my original function and I just want to factor it. So difference of squares and x cubed on the bottom. So I have points on my interval to find out what's going on at my vertical asymptote at 1, -1, and 0. So looking at x minus 1, that is 0 here. So to the left it's negative, and to the right it's positive. X plus 1 is 0 at negative 1. So to the left it's negative, to the right it is positive. And then x cubed is 0 here, so to the left it's negative, and to the right it is positive. So I'm really doing this because I'm interested in knowing what is happening at my vertical asymptote. So you can see to the left of 0 I have 2 negatives, which is a positive. So to the left of the asymptote at 0, my end behavior is increasing to positive infinity. And then to the right, I have 1 negative, so that means to the right of 0, I'm going down towards negative infinity. Okay, so now let's look at intercepts. If I plug in 0 here and here, I'm going to have negative 1 over 0, which is not allowed. So I do not have any y-intercepts because I have a horizontal asymptote at 0. We'll verify that in a minute. The x-intercepts are in the numerator at positive 1 and at negative 1. So positive 1 and negative 1, we have x-intercepts. Now let's go back down to that horizontal asymptote. I can see because I can't divide by 0, I know that I don't have a y-intercept, which means I must have a horizontal asymptote there. But let's look at it using long division just to verify. So x cubed into x squared minus 1. So that goes in there 0 times, which 0 times x cubed is just 0, and then I subtract and I'm left with x squared minus 1, which means my function x squared minus 1 over x cubed can be written as 0 plus x squared minus 1 over x cubed. So this is my horizontal asymptote, which I suspected I had. So at 0, I have a horizontal asymptote. So remember, we can go through our horizontal asymptote. It's just where the ends of our graph are going. So you can see I am crossing the horizontal asymptote because I do have some x-intercepts. But let's look at this, which is going to tell me my end behavior. So the limit as x approaches positive infinity of x squared minus 1 over x cubed. So big positive squared is still positive, take away 1, still positive. Big number that's positive cubed, still positive, and a positive over a positive is a positive. So that means that the end behavior as I go towards positive infinity will be above my horizontal asymptote. Let's look at the left end. So the limit as x approaches negative infinity. So a big number negative squared is positive, take away 1, still positive. A big negative number cubed is negative. Positive over a negative is negative. So that means that my left end is below the graph. Okay. Slant asymptote, none, because I can't have a horizontal asymptote and a slant asymptote at the same time. So now I just look at my even versus odd. So I'll look at f of negative x first. So that's negative x squared minus 1 over negative x cubed. So that's just equal to x squared minus 1 over negative x cubed. So seeing as how I don't end up with f of x, I factor out a negative 1 to see if I will then end up with f of x. So factoring out a negative 1, I do end up with this, which is negative f of x. So since f of negative x equals negative f of x, I know that they are symmetrical about the origin and therefore odd. Okay, so let's look at our first derivative. So our first derivative here, we're going to look at that for intervals of increase and decrease. So just factoring out that negative 1, I end up with x squared minus 3, which is a difference of squares, all over x exponent 4. So I have critical values at positive and negative root 3, and then at 0. Now remember 0 is a vertical asymptote, so I just want to mark that. Okay, and I want to look at intervals of increase and decrease. So let's just move this down now that it's in factored form. I'm going to look at -1 is negative in all of my intervals. Then I have an x minus root 3, which is 0 here. So to the left it's negative, to the right it's positive. I have x plus root 3, so that's 0 here. So to the left it's negative, to the right it is all positive. And then x exponent 4 will always be positive. So just looking for intervals of increase and decrease. So in the first one I have 3 negatives, which means it's decreasing. In the next one I have 2 negatives, which is a positive, which means it's increasing. 2 negatives is a positive, which means increasing. 1 negative means it is decreasing. So nothing can happen at the vertical asymptote, but if you look at negative root 3, I'm decreasing to the left, increasing to the right, which means there would be a minimum at negative root 3. So when y equals, I'm going to plug in negative root 3 into my original equation. Okay, and in doing so, I'm going to end up with -2. Let me just see here. Negative root 3 squared is going to be 3 minus 1 is 2 over, and this will just be -3 root 3. So I'm going to say that that's -2 over 3 root 3. So I have a minimum at negative root 3 and -2 over 3 root 3. And I'm not going to worry terribly about rationalizing that denominator. I want to know approximately where that is, and that's about at -1.7 and -0.4. So for the next one here, I'm increasing to the left, decreasing to the right, so this is a maximum, and I'm going to do the same thing. Y equals to root 3 squared minus 1 all over root 3 cubed. So that's just going to equal to positive 2 over 3 root 3. So then I have a maximum at root 3 and 2 over 3 root 3. So that's going to happen at approximately 1.7 and 0.4. So I can note those on my graph as well. So intervals of increase, it's increasing between negative root 3 up to but not including 0, or between 0 and root 3. We have to do those as two separate ones because 0, of course, is a vertical asymptote. It is decreasing on the interval from negative infinity to negative root 3, or root 3 to positive infinity. Okay, so we're going to put those on the graph, and then we're going to look at our second derivative to help us with the intervals of concavity. Okay, so you can see over here I have everything labeled, my max, my min, end behavior of my vertical asymptote and my horizontal asymptote. So let's look at our second derivative, and we'll do that in factored form. So factoring out of 2, I'm left with x squared minus 6. So that's a difference of squares, x minus root 6 plus root 6 all over x exponent 5. So you can see I have critical values at 0, which again is my vertical asymptote, and positive and negative root 6. So putting them in, 2 is positive in each one of these intervals. X minus root 6 is 0 here, so to the left it's negative, to the right it's positive. X plus root 6 is 0 at negative root 6, so to the left it's negative, to the right it is positive. And then x exponent 5 is 0 here, so to the left it's negative, and to the right it is positive. So 3 negatives make a negative, which means that this is concave down. 2 negatives make a positive, so this is concave up. 1 negative means this is concave down, and all positives mean this is concave up. So let's list out our intervals of concavity. So it is concave up on the interval negative root 6 to 0 or root 6 to infinity. It is concave down from negative infinity to negative root 6 or 0 to root 6. So we're looking for interval change or concavity change for an inflection point. So I have an inflection point here and here. At 0, it's a vertical asymptote, so it's not a point of inflection. So I have a point of inflection at x equal to negative root 6. So I put that into my original equation to figure out what the y value that goes with that is. So I'm going to have y equals to negative root 6 squared minus 1 all over negative root 6 cubed. So that's going to be a point of inflection at negative root 6 and negative 5 over negative 6 root 6. And just approximately so we can graph it, it's at about negative 2.4 and negative 0.3. So let's put that on the graph. So at about negative 2.4 and negative 0.3, so right about, we'll say there is an inflection point. Okay, let's look at our next point of inflection, which is at positive root 6. So I'm going to have a y value of root 6 squared minus 1 over root 6 cubed, which is just going to be 5 over 6 root 6. So again, that is at about 2.4 and about 0.3. So our other one is at positive root 6 and positive 5 over 6 root 6. So an inflection point at 2.4 and about 0.3, so right about, we'll call it there. So all we have to do now is just connect them with concave up and concave down. So let's do concave down. So concave down to the left of negative root 6. So looking at my inflection points, concave down there and kind of off to the end behavior. It's also concave down between 0 and root 6. So 0 and root 6 and going through that this area in here. So between 0 and root 6, here is my point of inflection. So it's going to be concave down in here, but it's going to continue down to connect my end behavior. Okay, concave up between negative root 6 and 0. So that's going to be in here. It's concave up, but then it's going to continue for the top of the graph because it needs to connect to the end behavior here. And the other place it's concave up is from to the right of root 6, so from this inflection point to the end behavior, kind of like that. Okay, so again, a lot of work, but all the graphing done without the use of a calculator. So we can go to our calculator to check to see if we're right, and you can see that that graph is pretty accurate. Okay, super long lesson, I know, but you guys can go ahead and look at the homework. When it comes to calculus, I will do derivatives. I'll do slant asymptotes. I'll even do intervals of concavity, which I've done several times. But to be honest with you, graphing is where I draw the line. Okay, end of a very long lesson. I hope it helped you. Nevertheless, there are your homework questions, and we'll do part 2 to this graphing lesson next.